Section 4.3.4.4, we're going to combine these two together simply because they're mainly the same thing. We're just introducing with section 4.4, we're introducing this leading coefficient a in front of ix squared term. So this is going to be some review of our factoring. We have a couple different special factoring patterns that we're going to be reviewing. We're going to talk through some new vocabulary maybe, or just refresh some vocabulary terms that we may or may not be familiar with. Hopefully you guys are familiar with them. But here are a few of them. Let's talk about polynomials. Poly, a prefix meaning many. And then we have here some examples of different types of polynomials. A monomial, mono, prefix of one, meaning we have one term. And a term, remember, can be just a constant, it can be just a variable, it can be a variable expression. Binomial would be sum of two terms, or the difference of two terms. Trinomial, now we're talking three terms. And then beyond that, we can just say polynomial for anything 4 terms or greater. Within each of these terms, when we talk about solving a polynomial, we're looking for some solutions. And specifically, our solutions that we're going to be interested in, or one of the types of solutions we'll be interested in, is when our polynomial is equal to a 0. And when we're equal to a 0, essentially setting our f of x value or our y value equal to 0, then we're able to, hopefully, in case of this trinomial here, ax squared plus bx plus c, we're hopefully able to factor that, or maybe we graph it to find the intercepts, or we use completing the square or quadratic formula. So today we're just going to kind of review the graphing part of this. So roots, a new term maybe for some of us. The roots are the solutions, specifically when our polynomial is equal to a 0. And in that case, we can think of roots as being the same thing as our x-intercepts. All right, some special factoring patterns. You've seen these before. Difference of two squares. What makes something a difference of two squares? Well, first, it's a binomial. Secondly, each of the terms are perfect squares. I can have a variable that's a perfect square as long as the power is an even number. I can have an integer on that b squared value as long as it's a perfect square. That would mean if I were to square root it, my solution would be a whole number. So you take all of your counting numbers, you square them, and you get perfect squares. So if I have a difference of two squares, I am able to break that expanded pattern into a factoring pattern, a plus b, a minus b quantities. In the case of a perfect square trinomial, now we have a trinomial expanded form, and we recognize a perfect square trinomial by looking at the roots of the leading term a squared, the roots of the last term b squared, and if we were to take those two roots, multiply them by 2, which is where this comes from, then we have what's called a perfect square trinomial. Some other concepts. This is a zero product property. Oftentimes we'll abbreviate this CPP. This is the property that I use to help me solve these polynomials when I'm looking for roots. And if I have factors multiplying together and their product is a 0, as in the case here of quantity x plus 5, quantity x plus 2 multiplying together producing 0, then that would mean that either x plus 5 has to equal 0, subtract the 5 and you get one of your solutions, x equals negative 5. Or you'd have x plus 2 equal to 0, subtract the 2, and you get x equal negative 2. So either of those would be values of x that would satisfy the condition there for that thing being equal to a 0. Those are roots. They are x-intercepts. So that's called the zero product property. All right, let's do a little review then on some factors. We've got a bunch of different problems here that we're going to go through. We will always check for that GCF, that greatest common factor. Oftentimes, factoring out the greatest common factor might help us in reducing our trinomials. So we're going to go pretty quickly through this, and I'm just going to run through these. If you want to try them right now and then come back and check the answers, you might want to pause the video and then come back and see the answers in just a second. So here we go. Our first trinomial x squared plus 14x plus 48. There are a couple different methods we can use to factor a trinomial. There's the trial and error method. And what that means is, well, I look and see if there's a GCF there. Nothing common variable can come out, no common coefficient can come out of the two coefficients or the constant. So there's no GCF. Then I just think about, well, what are the factors that produce x squared? Oh, that has to be an x and an x. What are the factors that produce 48? I have a pretty good list. I look at that list, and again, all these could all produce 48. And I look at those combinations of numbers and see how they might add together to make this 14. And then very quickly, we probably see that the 6 and the 8 works. They're both positive. So that's kind of the trial and error method that we use to factor. We do the same thing over here on B, and we get x minus 5x plus 1. Now, those two were trinomials. Now we get to a binomial, and we want to check, again, for a GCF. There are none here. But I look at this, and I see a variable with an even power. That's going to be a perfect square. Negative, that means a difference. And then 121, I've got a perfect square again. So this one is a difference of two squares. And that means it goes into a factored pattern of the root of m squared, the root of 121. One of them will be positive, one of them will be negative. Back over to a trinomial on D. Now we can have P and P. Here's one where I look at this and I recognize that it is a perfect square trinomial. Why? Because 144 is a perfect square that yields a root of 12. And if I were to take that 12 and multiply it by 2, I would get the 24 in the middle. Now, because the negative 24 is showing up there, I know that my factored form is going to look like p minus 12, p minus 12. And we often will just simplify that to be p minus 12 underneath squared. So now we introduce a leading coefficient here with 3. And I'm going to show you another way you might want to approach factoring. And I call this the X box. There's borrow from the clouds, very similar thing. But here's what we do for this one. Create this little funky box pattern. And we're going to fill in some values. Up on the top of the box, we will take the lead coefficient in the variable. In the middle of the box, we will take the coefficient in front of the x term. In the bottom of the box, we will take the product of the leading coefficient of x squared and the constant. So 3 times 8, 24. Now what you can do is you look for the factors of 24 that add up to a 10. And it has to be a positive 24. Or adding up to a negative 10. So if I take a negative 6 times negative 4, I get positive 24. Negative 6 minus 4 gives me a negative 10. So how do I create my factor form out of this? These two sets, 3x minus 6, form one of my parenthesis patterns. These two sets, 3x minus 4, form the other one. Now on the blue one, move this down here, I can divide out a 3 from that. And then I'm left with an x minus 2. And I still have my 3x minus 4. And I can check it. 3x times x is 3x squared. Negative 4x minus another 6x is negative 10. And a negative 4, negative 2 is an 8. So there's my solution, or my factored form of that trinomial. You can try it on this one again. 6x on the top, 1 this time. 6 and 15 is a negative 90 because it's a negative 15. Positive 10 minus 9 produces negative 90. It also gives me that positive 1. So 6x plus 10 we'll be able to divide out of 2. 6 6x squared plus x minus 15. All right, I'm just going to real quickly go through these other ones. We want to have plus 1 plus 7 there. Here we have a 3x and an x. I'm going to end up with a 7. So if I had a positive 12 minus a 5, I get that 7 term. There's the negative 20 term. We have a 5x and an x. And a 2 and a 3. A negative 2 gives me negative 10. Negative 3 gives me negative 13. Negative 2, negative 3 gives me 6. GCF can come out of this one. And when I pull the GCF out of this, I am ending up with a difference of 2 squares. We always want to factor. When we factor, we pull things down to its most reduced form. 8, let's see, we can pull out a 4, it looks like, here as a GCF. So a 4. Now, before I do that box thing, I always want to pull the GCF out. So we're going to pull the 4 out, and we get 2x squared plus 7x minus 30. And now I'm going to just focus on that for my box. Just to show you the process again. 2x, 7, negative 60, and we want, let's see, we got 2 and 30, or 3 and 10. That would work. Sorry, not 3 and 10. 3 and 20, 4 and 15, 5 and 12. So 12 minus 5 gives me a 7. 12 times negative 5 makes negative 60. So 2x plus 12, I'm going to be able to reduce those by 2. 2x minus 5 we will leave alone. Now what I don't want to forget is that this 4, this GCF that we pulled out from the beginning, needs to be included in the solution there, or in the simplification. And then finally, another difference of 2 squares problem. And there we are. A little factoring review. Why are we doing the review of the factoring? So that we can solve for the roots of the equation. Or the x-intercepts. And we're going to learn in just a little bit. There's another name that we have for these, and that would be zeros. The zeros are the function, the values of x that make the function equal to 0. So we just go back and we do our little factoring review here. And I recognize that I can factor x squared minus x minus 42 as those two factors. Now I introduce the equal and 0 part, so now I'm solving. I'm looking for the value of x that makes this thing true. 2 factors that produce this, so I can set each factor equal to 0 using 0 product property. And there would be my 2 possible answers for that problem. Those are the roots, again, of that polynomial, the x-intercepts. This one, factors, x minus 5x plus 3. And again, set each of those factors equal to a 0 and solve for x. And we get the same thing here. Taking a little shortcut. Get 2 or 1. So we just added just this equation component to our factoring and then use 0 product property. There's that new term. The zeros are the values of x that make our function equal 0. And again, if we have a function value that equals 0, if y equals 0, and you're finding x-intercepts. What's different about this equation? equation is no longer does it say 0 equal, it now says y equal. So what I'm hoping that you understand is if I ask you for zeros, I'm asking you to identify that the y value needs to become a 0. You're trying to make 0 with these x's. So I went ahead and made y equal 0, and I factored, and we used our zero product property to discover that I could be either a -7 or a 4, and those are the zeros of that function. And then real quick here, this one's interesting. Two identical factors, so really, I have only one 0 when x-intercept. That's a parabola that's opening up and hitting the x-axis at one spot. Actually, x equals 2, so its vertex would be 2, 0 at that point. You start to recognize those types of things. So look for the vertex. Where would it be? One more. And once again, finding the zeros. X equals -6 or 1. We'll be proficient factor orders when we're done with this. All right, solving. So far we've seen find the roots, we've seen find the zeros, now we see solve. We're essentially doing the same thing. We're looking for the values of x that produce this value on the right-hand side. In this case, it's 0. And you'll notice on B, it's different. So we're going to have to think about how we would create a 0 on part B down there. All right, I'm going to go ahead and go back to my box on this one. We have a 4x, we have a -17, we have a -60 because of 4 times -15. Factors of -60 that produce a 17, 20, and 3. -20, +3. So I have a 4x minus 20 that I can reduce. I have 4. And I have a 4x plus a 3. So we get x minus 5 and a 4x plus a 3. Now I'm just showing the box method. You don't have to do that. You could do the trial and error thing. You'll get the same answer. And then because of our zero product property here, we get 5 or -3/4. So we haven't really seen an example where I had a binomial that had a lead coefficient. Before, we might have started to recognize, hey, if I just take the opposite of this number, then I always get my answer for what a 0 is. And that will be true if your lead coefficient in front of that x is a 1. If it's different, we got to just set up this problem where I solve and then divide it. And that's where we're getting that value of x. Part B, don't have a 0. So we need to create a 0. Let's move all of our like terms to one side of the equation. So that means my x's are going to go hang out with the x's, and the constants are going to go hang out with the constants. And when I do that, I have equals 0 over there. I have to remember to include the equals 0 part. So 22 plus 14 is 36 x's. 60 plus 48 is 108. And now this equals 0. I look for my GCF. Those are all divisible by 3. So I pull out the GCF. And then once again, that 3 hangs out. I recognize this is actually a perfect square trinomial, so I end up with that. Then we're doing zero product property. Now, this is a factor. However, it does not include a variable x, so I do not have to set that equal to 0 to solve for x. So what I don't want you to do is this, because that's actually not true. There's no variable to solve for there, so I don't need to actually worry about the 3. If the 3 had an x with it, 3x equals 0, then I would solve for x. So really all we're looking for is this. That is undo squares by taking the square root, and then we get x equals -6. There are the zeros or the roots for that particular problem. All right, lastly, we get to some application for this. So these quadratic forms, we've seen some examples of like an object in flight. We can also have examples that deal with like maximizing, minimizing areas. So we'll see how a quadratic comes into play here. So remember, a quadratic is simply I end up with an x squared term somewhere in my equation. All right. With careful reading of this problem, we're making a square frame of uniform width, means the same width. So that uniform means that this width here, we'll just call W, is the same all the way around. All right, that's uniform width. It's a square picture, and the picture has side lengths of 2 feet. So here are the 2 feet representing, so inside of here, this area right there is the picture. Then we get this total area of the frame is 5 square feet. What is the length of the sides of the frame? So we have to be careful when we're reading the problem. In particular, this part of it, the total area of the frame is 5 square feet. So the frame is the darkened area. And we got to be careful that we don't interpret that to mean the frame including the picture, because that's not what this is stating. This is stating simply the frame's square area, footage is 5 square feet. So it's all of that dark area is 5 square feet. So we have these dimensions of x and x that include both the frame and the picture. We have these dimensions of 2 that include just the picture. Well, what makes up this area, if we look at the entirety, including frame and picture, so I'm looking at this whole thing here, the area of that would be equal to the length times the width, or in this case, x squared. That area is made up of 2 things. It's made up of the area of the frame. So we know that this area, which is equal to x squared, is made up of the area of the frame plus our area of the picture. All right. So let's see if we can associate some numbers with that. Area of the frame. Well, we were told the area of the frame is 5 square feet. The area of the picture. Well, the area of the picture is made up of this 2 by 2, so we know that that is 4 square feet. Therefore, our total area is 9 square feet. So here's the quadratic. We simply take the square root of both of those, and we're taking square roots, which means we get 2 answers, plus and negative, plus and minus. But you can't have a negative length on something, so we just take simply the positive value of that, and we can find that the length of the sides of that frame are going to have to be 3 feet. Another application problem. We have the stage. The dimensions of the old stage were 30 feet wide and 15 feet deep, and the new stage has a total area of 1,000 square feet. So on these drawings, we're going to define things often with a picture. So let's draw a little sketch. So 30 feet by 15. So the length, which is the right and left part, is twice the depth, which is the up and down part. So we're defining that this is our depth, and this is our length. That little apostrophe thing, that's our symbol that we use for representing feet. So that's our old stage. And it says that we're going to take a new stage, which has 1,000 square feet, and the dimensions of the new stage were created by adding the same distance x. So they're telling us, definition, defining our variable there. We're adding same distance x to the width and the depth. So we're not tearing the old stage down. We're simply adding onto it by increasing the length or width and the depth the same value. So if that's the case, it's like you are going to maintain one of the widths and one of the lengths as currently shown here. So let's assume that we're just going to leave the stage as it is, which means we have a fixed dimension this way and a fixed dimension that way. And we're going to simply expand this by adding some new width and some new depth and creating this new stage. So we would love to be able to find out this value of x. Well, we got to see in our picture what does x represent here. X says that x represents this new distance that we've added to the width and to the depth. So we have our length or width. I should probably use the same variable that they're talking about here. This is a width, not a length. So width. So we have our existing width of 30 feet. And then we add on to that this length. We don't know what it is. We're just saying it's an unknown length of x. We had a dimension here for our depth of 15 feet. We added onto it that same dimension of x. Put the stage out further, made it go wider in the right direction. All right, so we have that. We were told that the area of the new stage is 1,000 square feet. And this stage is in the shape of a rectangle. And so we know that that has to be made up by width times depth using their dimensions there. So we have some work to do. We need to know what this new distance is. And we need to know what this new distance is. So hopefully maybe you started this, and up to this point you kind of followed along. Maybe you pause right here and see if you can come up with what those new dimensions would be, and then come back and check in just a second. So I'm going to keep going. We're going to discuss what these dimensions might be. All right, we're going to take this width dimension. We know that it started with 30. We added something to the 30. We added this width of x. So that means this new long dimension along the front of the stage has to be the original 30 plus this new dimension x. Same thing is happening on the depth of the stage. It started with the original 15, and then we added this new dimension x. Those two then define the length, or the width, and the depth of our new stage. So these become our w and d for our equation over there on the right. Our equation of 1,000 equals w times d now becomes 1,000 equals 30 plus x times, that's the w dimension, 15 plus x, that's the depth dimension. So we should always start out with our generics, like that's a generic formula for area of a rectangle, filling in the things that we know. Now we can see right here we have a quadratic. Well, maybe we don't see that it's a quadratic. But I have two binomials multiplying together, which means those x's are going to multiply together to become an x squared. All right, when we've been solving this before, we tried to have a 0 on one side. So if I tried to get a 0 on one side right here by subtracting the 1,000 to the right, I have a problem. Because on the right-hand side, I'm not in expanded form, I'm in factored form. So we're going to have to kind of take ourselves out of the factored form. We're going to have to take this out of factored form, put it into expanded form first. If we did that, foiling, get 450, 30 times 15. And then we have 30x and 15x, 45x's, and then x squared. Now I can see if I move the 1,000 over, I'm going to get negative 550 plus 45x plus x squared. Now I'm in a place where I see a 0. That's good because now we can factor this thing if it's factorable. All right, I think it's factorable. If we were to factor this, we would get an x and an x. And let's see, 55 times a 10 is a 40, is a 550. And we want it to be that. I know it looks different because we're kind of backwards from what we're used to seeing. So maybe what you want to do is, what if we just flip this thing? Put the x squared first, put the 45x, then the 550 equals 0. Maybe it's easier for you to see what we just did there. We had 55, we're going to take 10 away. And it's the same thing that's going on over there, it just looks different. Here's my 55x, here's my minus 10x. Here I have my 55x minus 10x. Oh, I should have had a negative. I wanted the negative 55. Got to pay attention to that over here. All right. We got our x, we got our x. 55 is positive. Our 10 had to be negative. And then we do that. 55 minus 10x. There's my 45. Just looks, again, different than what we have on the left-hand side here. And we get zero product property. Tells me that one of my distances is 10 feet. And the other one, I don't know if that makes a lot of sense. Can't have a negative length. So even though that is a 0 for that polynomial, it doesn't fit the condition we have for this word problem. And so we have to take the positive value of x equals 10. That would be the length that we have to add on to the width and the dimension of our stage, depth dimension, to come up with this new 1,000